Good morning, Astronomy 1010. Welcome to the 9th lecture and the 9th lab, where we will explore and compare the terrestrial geological processes of Earth, Mars, Venus, Mercury, and we'll even include the moon. So today's lecture is all about terrestrial geology and planetary geology. We'll deal with Jovians at a later time. Today's lab, as someone asked, is the 9th lab, which is on lunar craters and lunar features. That's a fun and jazzy one. You're going to go to lab 9. You're going to need your lunar features data sheet here, which I'm going to hit print on mine right now before we get started. You guys might want to do the same thing. You'll also need this moon map, and I've got one. I've got a physical copy here, but I've scanned it for you guys in 2 halves. So you can either print it or you can use it right on your screen, but you might have to bounce back and forth. It'll have the names of the craters and some other things. So today's lab is fun and easy. We'll just get to kind of know the craters of the moon. Okay, that's printing. Let us hide the trolls, because we don't need no trolls clogging up my video screen. Okay. Now that I'm dealing with humans, I will go to speaker view and lock on myself. And I guess we'll give these notes a heading here. Actually, guys, if you can give me one more second, board's a little crusty today. Let's just get some of the extra kick off it. Okay, we're just about there. Sorry, I was a little running behind this morning. Okay, now that we've got a squeaky clean board. Oh, I'm out of focus. That's not good. Let's get that Logitech up and running, because we cannot have autofocus issues during this lecture. That was going to slow me right down. This may kill my audio. Sometimes opening Logitech throws off the audio. Come on, baby. Okay. Okay, autofocus is deactivated now. That should be good. All right, today's lecture is on terrestrial geology. Basically, how do the interiors of terrestrial geological planets work? We're going to mostly exclude atmospheres. That'll be covered at a later time. Since we only have our solar system to work with, we're going to be limited to, wait for it, 5 terrestrial objects. Even though the moon is technically not a planet, you'll remember me saying during our last lecture that the moon is an obnoxiously large moon for the terrestrial zone. In fact, Earth's moon is comparable in size to a Jovian moon. And because of that, and because we're desperate for data points, we can actually analyze the moon in terms of planetary geology, just like the other planets. So we're going to kind of put the moon on the same playing field here. Now, you guys know what everything is, right? What's this planet?
Venus.
Fuck. Okay, well, we're going to have to slow this one down.
Oh.
This is Venus.
Oh. I thought that was Mars because it was red.
Earth, this is Mars.
Is the first one Pluto?
No.
Mercury.
Mercury, that's right. My very educated mother just served us nothing. So this is Mercury, okay? And this is the moon, obviously. Too many M's. Mercury, Venus, Earth, Mars, and the moon. The reason why the image of Venus is red, Joel, The surface of Venus is actually jet black, but we've only seen the surface of Venus maybe one time from a spacecraft that landed on its surface in the late 1970s. And most of the surface of Venus would be a mystery were it not for the fact that we use radio waves to bounce radar off the surface of the planet and map its features. So what this is this is actually a radio map, which has been false colored orange to show the intensity of reflected radio waves. So it's a little bit of a cheat, the color of Venus here. If you actually look at Venus, let's try to do this right. If we look at Venus from outer space, you see the very thick cloud covers, and it kind of has a whitish yellowish appearance. So here's the nice Wikipedia image. Let's go to Wiki on Venus. Come on, baby. This is probably what I should have grabbed. This is the picture that you see from space of Venus. It's got some yellowish, whitish clouds covering its surface. Very difficult to see the surface. I picked a surface photo because we're supposed to be talking about terrestrial geology instead of atmospheres, so I thought that would be appropriate. Okay, the first thing I want to do is I want to take some notes where we rank the planets not by their distance from the sun, but by their radius, which is going to turn out to be one of the most fundamental, important properties of a planet. So let's start with Earth. Earth is the biggest terrestrial planet. And it has a radius, you may recall, of 6,400 kilometers. That's the biggest of the terrestrial planets, followed by Venus, whose radius is 50 kilometers. Because of the closeness of Venus and Earth in terms of their size or radius, they're sometimes called sister planets. And these would be examples of what we might think of as a big or a large terrestrial planet. So Venus and Earth are going to be your quintessential large terrestrial. Next up on the list, of course, is Mars. Mars is somewhere in the middle. It's a medium-sized terrestrial planet. It has a radius of 3,400 kilometers. And like I said, Mars could be thought of as a medium-sized terrestrial planet. And finally, Mercury and then the Moon could be considered examples of small terrestrial planets. Mercury has a radius of, wow, I think it's 2,400 kilometers. Although I'm having some doubts, but I think it's 2,400 kilometers. And the Moon, this today is around 1,700 kilometers. Mercury and the Moon are classic examples of small terrestrial planets. Believe it or not, how big a terrestrial planet is will determine tremendous amount of details about how many features it has, how much active geology it has, and even in a sense, whether or not it's capable of supporting life. Planets that are more likely, but not always more likely to support life are bigger ones. Smaller ones are usually basically just rocks in space. Okay, so let's think about the Earth for a second. The Earth has a radius of 6,400 kilometers. And I'm guessing that at some point you guys had to take an Earth science class like I did in junior high school or something. And if you ever took an Earth science class, you probably learned some basic concepts about the interior. Whoa, sorry, my mouse just froze there. You probably learned some basic concepts about the interior structure of Earth. Like before I knew anything about anything, I somehow knew that there were 3 layers to Earth the crust, the mantle, and the core. And I'm hoping you guys knew that, but maybe you didn't. How can we possibly know what's inside the Earth? If you think about Jules Verne's journey to the center of the Earth, some intrepid explorers they burrow into the interior of Earth, and in the center of the Earth, they discover dinosaurs, I think, or something that's like dinosaurs. Have humankind ever journeyed to the center of the Earth, like Jules Verne suggested? Mathis says no. Then how far down have we gotten? What do you think the deepest we've ever burrowed into the interior of Earth is? Who would go the deepest into Earth?
There's someone that mines.
Andrew, you're a little garbled today. Did you say miners?
Yeah.
Your audio is pretty messed up. I don't know what's going on, but so he's suggesting miners. That's one idea for sure. They go down into caves. Oil drilling exploration is another one that comes to mind.
James Cameron in the Marianas Trench.
Right, but he was still on the exterior of Earth. He definitely went to he went to the deepest point in the ocean, Joel, and he was getting so deep that he was sort of entering Earth. But even still, the Marianas Trench is about 7 miles, which is, I don't know, not many kilometers, right? 7 miles to kilometers.
About 10.
Right.
11. So it's
still
like a sixth of the way through the.
He did not go below the rock layer. Okay. The deepest point ever constructed on Earth is actually in the or in Russia, former Soviet Union. It's known as the Kola Super Deep Borehole. And the Kola Super Deep Borehole was a scientific drilling project that the Soviet Union conducted to sort of measure temperatures and pressures and chemical composition of the rock layer of Earth, and they got down to about 12 kilometers. Today, the site is no longer in use. It's abandoned. Here's a commemorative stamp showing them drilling 10 kilometers or so down into the interior of Earth. Today, it's just basically an abandoned scrapyard. So it's no longer in use. And the actual super deep borehole itself is shown here. It's all welded shut and it's just sitting there collecting rust in the scrapyard. That is the deepest man-made point this scientific expedition ever constructed. And according to this, they went down 12,262 meters, which, as you dimensional analysis lovers will remember, is about 12 kilometers. Let's take a note on that and commemorate the Kola super deep borehole. So if we ask, how deep have humans, we could say, explored or drilled into Earth? The answer is the Kola super deep borehole. Today, no man-made structure has gone deeper, and it's approximately 12 kilometers. Class, what percentage of Earth's radius is that? That should be something you could do with your calculator pretty quick, right? Mind taking out your calculators and dividing that?
About 18%.
18%?
No, sorry.
No effing way is 12 bucks, 18% of 6,000 bucks. Where's my?
I was doing 12 into 64.
Oh, I see. So it should be 0.018 then, right?
0018 or 018, yeah, something like that.
Can we just divide it? Oh yeah, you're right. 0.018, or roughly 0.002. Joel, what percentage is that? We're in
0.2.
0.2%, so 0.2%. In other words, we've hardly explored jack shit when it comes to the interior of Earth, if you think about it, right? We've barely even penetrated that crusty surface. So then, Mathis, I don't know if you can understand my point here, but how the hell are we supposed to know what's inside the interior of Earth if we've only actually explored 0.2% of it? How would scientists know what's at the center of Earth? I thought that might be a head scratcher.
Because they know how the planet was created in the first place and what. Well, they don't know, but I don't know.
Well, the density and the mass definitely shape our expectations of the fact that there should be rock on the outside and metal on the inside. But the real way has even better, Enrique. Hey, show of hands here. How many of you guys felt that earthquake this weekend? We actually experienced an earthquake in Rhode Island. That was pretty cool and very timely.
When?
We're shooken out of bed because of that.
I was in bed too, and my bed was like rocking back and forth, and I was like, holy, I was in a building, I live in a building downtown, and since we live in Rhode Island, it's extremely rare to experience that. It wasn't too violent, Cam, but I was kind of like in one of those half awake states. So my bed started rocking back and forth, and I shouted to my partner, Jordan. I was like, I think we just experienced an earthquake. And she's like, no.
When was
no
this?
kidding. Huh?
When was it?
Saturday, right? Was it Saturday?
It was Sunday.
It was yesterday.
Oh, was it yesterday? Yeah, it was yesterday. Geez, I can't even remember what happened this weekend. Too many brain cells got zapped. Okay, so wait a minute. Was it yesterday?
Yeah.
Yesterday morning.
Yesterday morning. Thanks, Kelly. And so you guys all felt that, right?
No.
I slept through it.
Joel, you could have missed it if you were in a deep sleep, but if you were awake.
I live really close to you.
Yeah,
'Cause
exactly.
I'm by the post office, so I don't know why. And I was up pretty early.
It felt like my bed was getting pushed back and forth. I was sort of, yeah, I don't know.
I felt it when I was in my house, but then when my dad came home, he was walking the dogs outside. He was super confused when I said we had an earthquake, so he didn't feel it. So if you were outside, I don't think you felt it.
Actually, Kelly, this is a really good point. Because I asked my father about it. I went to see my dad in Smithfield, and I said, did you feel the earthquake? He's always out in his garden, and he said he did not. So the theory that I came up with, which could be complete hogwash, but the vibrations might have been so gentle that if you were standing outside on the ground, you didn't notice it much. But I was in a building, and the building was rocking and swaying, and it was probably the vibrations of the building that we really noticed, right? Because these old buildings here in New England weren't designed like they are in Los Angeles. They expect those buildings to go through earthquakes. But nobody, when they built these old brick buildings or whatever, they didn't anticipate earthquakes leveling them, which actually makes them quite dangerous, right? God, I'm glad that 5 stories worth of bricks didn't collapse on me. That would have been horrible. So if it had been a little more violent, it could have been a very dangerous situation for some of us. But it sounds like a common theme with all of you folks out there is that the ones that were inside felt it the most. I was even wondering if I had been laying down, if I would have noticed the gentle shaking back and forth. Standing up might have been a different experience.
So I hit Buzzards Bay just after 9 yesterday, and it was 3.6.
Yeah, unusually strong for here. We live, as you'll discover, on some of the oldest tectonic rock on planet Earth. So it's not unheard of for an earthquake to happen here, but it's not very common. One of the weird things about living on old sort of bedrock that doesn't have a lot of faults in it is that geological pressures can build up for an extra long time. And when you do sometimes have a random earthquake around here, it can be quite violent. So we're lucky that it wasn't any crazier than what we experienced. Kind of cool to hear that so many of you experienced it, though. Okay, so the answer, why did I mention this? Because The study of earthquakes is how we know what the interior of Earth is all about. That kind of came at a good time for me. We study seismic waves. So let's talk about earthquakes and what happens during an earthquake. During an earthquake, pieces of Earth's crust, which are constantly, or we should say later its lithosphere, are pushing against each other and pressing against each other and building up intense geological forces. And they snap over the top of one another, or maybe side to side, and send these vibrations that travel through the rock. And they're basically in the form of waves. They're very similar to the kind of waves that you might see me generate with a slinky here. Ooh. I usually do this demo when I have a live class, but it's kind of hard to do it over the computer here. When I generate a wave on a string using this slinky, I tend to generate something called transverse waves. A transverse wave is a wave where the displacement, and here the displacement is the spring kind of going like this, okay? If the displacement is up and down, but the wave travels sort of side to side, that's called a transverse wave. So waves on a guitar string would be examples of transverse waves. There's another type of wave that's possible to create called a longitudinal wave. And that's where you have some density or some medium like this spring here, and you pull it back and you create a compression. So in one zone, you have a little compression followed by an expansion or a rarefication. And I might even be able to demo this. Let's see if I put my black backdrop here, I'm gonna do a compression and boing. You can actually see it better if you stretch it out more, but you can do a compression followed by a rarefication, and you can actually see the wave travel back and forth. This demo really needs to be done in person so I can stretch the spring out across the classroom. Since that's going to be a fail, let's go ahead and look at cartoon pictures again. So here, oops, sorry. Here you can see a transverse wave. That's where the displacement is perpendicular to the string. Here you can see a compressional wave where we have a compression traveling down the spring followed by an expansion or a rarefication. And they're both describable with sine waves and cosine waves from mathematics. These types of waves also happen in rock. In earthquake science, we study S waves, which are the transverse waves. They sometimes call them shear waves or side-to-side waves. And then we have P waves or pressure waves, which are where the rock compressions travel through Earth. Now, what's interesting about these seismic waves is S waves and P waves propagate slightly differently through the interior of Earth, as this picture here demonstrates. The S waves and the P waves both can travel through solid rock, but we know that there's a certain layer of Earth's metallic core that is in a liquid state. The liquid metal core blocks the S waves, but it allows the pressure waves or the longitudinal waves to pass through. So every time an earthquake goes off, like the one that we had this weekend, there are seismographic stations that are set up all around Earth that measure those vibrations as they travel through Earth. And as the scientists collect the ratio of S waves to P waves, they compare them to all the other stations, and that helps them model how big the liquid metal core of Earth is. This doesn't give you incredibly fine resolution, but at least gets you a basic sense of where the rock stops, where the metal begins, what parts are liquid and what parts are solid. So that earthquake, anyone find it funny this happened in 2020? Yeah, this is appropriate for 2020. But remember, there's a good side to these earthquakes. They help us learn about science. So the answer to our conundrum then, let's just write this down so we don't forget. What we know about the interior of Earth, let's try that again. The interior of Earth we know about through the study of seismic waves. In fact, this is so important that scientists also put a significant amount of effort into trying to study earthquakes on the other terrestrial planets. Except it turns out that one of the difficulties is that Earth is the most geologically active of all the planets. So for instance, we put a seismograph onto the moon when we landed there, but unfortunately we didn't really detect much in the way of moonquakes. Today, there is a spacecraft which landed on Mars pretty recently called the Mars InSight mission. And its entire focus is to study Marsquakes. So I like to tell you guys about cool space missions. One of the most recent spacecraft that we landed on the surface of Mars is the spacecraft called the Mars InSight lander. And it's basically a hypersensitive seismograph that drills down into the Martian surface and tries to detect Marsquakes. Now, we believe Mars is geologically dead and we do not expect any major earthquakes to erupt on Mars, but we still are looking for the tiniest of tiny vibrations that we can find to try to probe the interior of Mars's surface and just find out how frozen out its interior is. Supposedly, this instrument is so sensitive that it can detect vibrations from meteor impacts which strike the other side of the planet. So if a rock from space strikes Mars on the antipodal side, this thing will be able to detect those vibrations in the rock from the other side of the planet, which is super incredible. So read more about Mars InSight if you're interested in this kind of thing. Okay, so what have we learned? Let's start with the interior of Earth. And it turns out that there's two different ways for us to study the interior of Earth. And we're going to make some notes on that now. One way is the way that you learned in your Earth science class, which is break it down into 3 parts: crust, mantle, core. But there's another way to do it as well. Let's title this module "The Two Methods or the Two Ways of Layering Earth." And I think we're going to do this as a little chart or table here. The first method, the traditional method, is by density. And you guys might remember from last week's lecture that density is pegged to chemical composition. Does anyone remember why? Why does density have something to do with chemical composition? I don't like my D there. Does anyone remember why I can say that density is the same thing as chemical composition? Can anyone have
Well,
a...
density is how thick something is. So if you have granite, that's thicker than, like, say, ice.
I wouldn't say thick. Thickness is a linear dimension measured in meters or kilometers. Density is measured in grams per cubic centimeter. You cannot say that, Joel. It's just not true. Science is about cleaning up your speech. Why is density related to chemical? What the shit do I even mean by chemical composition?
Like whether or not it's a Jovian or a terrestrial?
No, that's like a planetary class. Chemical composition is what atoms are you made out of?
Well, if you have a 5-pound bag and you put 5 pounds in it, but then you try to stick 10 pounds in it, the 10 pounds of stuff in the 5-pound bag is going to be denser than the 5 pounds.
Well, but pounds are a unit of force, so I don't like that so much either.
Yeah, I'm trying to figure out how to say it.
Well, what I wanted you guys to say to me is that the reason why density is a tracer of chemical composition is because we discovered when we looked up which one is the high res version here? My internet's really sluggish today. Just
Part of-
like me.
Part of me wants to say like the mass, but like the greater the mass, but I don't think that's right
On.
because mass is like volume, right?
No, mass is totally different than volume. But mass divided by volume is what we mean by density. All right, you guys forgot this already, so I'm going to keep telling you the same thing over and over again until you learn, okay? Density is related to each individual atom on the periodic table. Every atom on the periodic table has a unique density. And therefore, whether something is made of rock or metal or gas, you can identify it based on its density. Notice if we scroll up here that the density of beryllium is 1.85 grams per cubic centimeter, where the density of magnesium is 1.74 grams per cubic centimeter, and calcium is 1.55 grams per cubic centimeter. Each atom has a unique density structure. And because of that, density is a tracer of what a planet is made out of. There's another way to do it. And the other way to do it is by strength. Another word for strength could be rigidity or even plasticity. I don't think I can spell plasticity now that I think about it. Plasticity. No, I don't think I did that right.
Combined plastic, yeah, like that.
Okay.
Plastic City.
Wow.
Plastic City.
Plastic City. Thank you, Joel. I'm never going to forget that. That's a good mnemonic. All right. Plasticity. So, okay. If we do it by density, then Earth basically can be broken down into 3 layers with major density changes. There is the crust. The crust is low density. And that means it's mostly made out of silicate rock. I'll explain what I mean by silicates in just a moment. As you drill down into the Earth, or as you go down into the radius of Earth, you suddenly hit a boundary where the density goes up quite steeply. And that's a new layer that we call the mantle. The mantle is kind of medium density. And it's a mixture of silicate rock, which has been under great compression, but also a higher concentration of metals, all right? And then you get to the core. The core is high density. And that's usually made of metals. In particular, the metal iron and the metal nickel. The symbol for iron is Fe, by the way, ferrous. Let's look at the other method in a jazzy diagram here. Let me give you guys a second to catch up to me.
So it's iron and what's Ni?
Nickel. Let's
Nickel.
write those. Let's write those underneath, Jake. That's actually a good idea. Iron and nickel. Famously, all terrestrial planets are thought to have an iron-nickel core. If you want to know why are those 2 metals the ones that make up the cores of planets, it actually turns out to have a deep connection to the death of stars and supernovae. When supernovae go off, they tend to produce a tremendous abundance of iron that gets ejected out into the interstellar medium. So when planets form from the cosmic gas in between planets, there's higher concentrations of iron and nickel than there are of other types of metals. It has to do with the death of stars, why the cores of planets are made of that. You can learn about that, Kelly, in my Astronomy 1020 course next semester. Okay, there's a pitch for Astronomy 1020. Let me show you guys a diagram before we go any further of the two methods of layering Earth. I think this photograph, which is not in your books, is wonderful. Take a moment to look at this. I want to grab my stool here. I just hit myself in the shins. Ow. Okay. Ouch. So on the left-hand side, you see the kind of classic crust mantle core structure. And now you know that what you were layering Earth by was by density or chemical composition. Notice that there's another way to break up the exterior of Earth, and that's by how strong or rigid it is. I mean, guys, think about it. Thanksgiving, right, is coming up. And when people talk about crust, let's face it, when you hear the word crust, you're thinking about that other crust that's so important to us in Thanksgiving time, and that's pie crust, right? And if you think about what pie crust is the frozen, crispy, brittle layer of a warm, gooey interior of apple pie, right? And when we think of the crust of Earth like pie crust, we're actually using the wrong terminology here. We should call this pie lithosphere. This is essentially what a lithosphere is. A lithosphere is the crispy, frozen, brittle outer layer to a planet. So while we think of the crust as being like that, it's really the term lithosphere. And you'll notice from my diagram that the lithosphere and the crust are not exactly the same thing. You can see that the crust extends down deepest about 75 kilometers, but the lithosphere goes deeper to about 100 or 300 kilometers. And what that means is at some point as you travel through the crispy outer layer of Earth, the density suddenly goes up tremendously because of the increase in metal content or something. But even though the density structure is changing, it's still frozen and it's a solid outer layer. Now, I don't want you to get some goofy idea like the layer underneath is full of a pool of lava or something. This layer underneath, the asthenosphere, is warm, convective rock, but it's in the solid phase, or I guess you might say a plastic phase, where it can morph around. The book actually asks you to consider the asthenosphere as being a substance that's like silly putty. Most of us would say that silly putty is more solid than liquid, but silly putty can flow like a liquid. So the asthenosphere is rock that flows. And that plays a big role in planetary geology. It also plays a big role in the earthquake that you experienced this weekend. So introducing a new vocabulary term. The lithosphere. The lithosphere is the hard, brittle, frozen outer layer of a planet. We'll be discussing the lithosphere not only of Earth, but also of Mars and the other terrestrial planets as well. Underneath it is the asthenosphere. The asthenosphere consists of warm, convective rock on which the lithosphere floats. The lithosphere actually floats on the warm convective asthenosphere, kind of like an iceberg or a sheet of ice, and it crashes into other layers of rock as well. The asthenosphere is rock that flows. That's how you should think about it. The asthenosphere is rock that flows. Together, the lithosphere and the asthenosphere are what create and drive plate tectonics. This is one of our fundamental geological processes, and it's the process that's most responsible for earthquakes. Okay. Underneath this, we have a more solid layer called the mesosphere. The mesosphere is solid rock, but it may have some convection in it. The jury's a little bit out on that. And then the core, which is the metal core, is divided into two layers. There is the outer liquid metal core, and then the solid, or the, I guess I should do these the same way. The inner solid metal core. Let me just take a moment for you guys to catch up to that. These notes are kind of important.
Brendan,
Yeah.
did you read that article I sent you?
When did you send it to me? Apparently not. Oh,
Saturday? You responded to it.
right. I remember it was cool, but I remember I was doing something when you. Oh, shoot.
Yeah. Scientists discovered bizarre hell planet where it rains. Rocks and oceans are made of lava.
Oh, no, I loved that title and I wanted to come back to it, but it was too early in the morning for me. And then when I woke up, oh, right. Joel, here's the problem. When you, oh, you did send me the link. Sorry. I clicked on the picture and the picture just showed me the picture. So this would be an example of a world, Joel, that has an even thinner lithosphere than Earth does. Oh, it's Earth-sized. I was expecting it to be a little bigger than Earth. Maybe it's a little bit closer to the sun, and that's why. Okay, this is cool. I'll look at this during my tea break. It's
Right.
up on my phone right now. Has everyone got this? Andrew, how you doing?
That
That sounded like this.
sorry.
It's okay. It's not your fault. I don't know if it's your connection or your microphone, or you spilled some water on it or what, but Andy, give me a thumbs up if you're done. All right, cool. Oh wait, we got two Andys here. There should be Andrew and Andy. We're gonna fix that from now on. Sorry about that, guys. All right. So at some point I want to talk to you guys about how magnetic fields are generated. That turns out to be deeply related to the fact that Earth has a outer liquid. Actually, first let's just talk about something. What do you think is the warmer layer of Earth's interior? Is the outer liquid core hotter, or is the inner solid core hotter?
Would it be the outer?
Why would you say that?
I feel like
What's your reasoning is all I'm saying.
I thought it would I don't think I thought it would
Wait, Frank, I
Mhm.
think you were just thinking because it's liquid, that's why it would be hotter, right?
yeah.
Whereas normally, like on Earth, colder things freeze, right? And then warmer things melt. Is that sort of what you were thinking?
Yeah,
Well-
that's what I was going for.
I wasn't looking for anything more complicated than that. But there's an issue here, Frank. When we go down into the interior layers of a planet, we not only change temperature, but we also change pressure. And pressure and temperature can have a funky effect on the state of matter. Have you ever had to, swim inside of one of those deep pool? Like, have you ever gone into like an Olympic-sized swimming pool where they've got the deep end?
Like McDermott Pool in Warwick?
How deep does that go? Is that a 12-foot at the deep end?
I think so.
All I know is when I was a kid, I used to play the game where you throw a quarter in the bottom of the pool and then you try to dive and get the quarter. And I remember I couldn't really do it at an Olympic swimming pool. It was, if you go down 12 feet, you can really feel the pressure of that water over your head, and it's pretty intense. Now, I haven't tried to do this since I was a little kid. I'm probably even less athletic now than I was then, but I remember that I had trouble getting the quarter from the bottom of the pool in an Olympic swimming pool. And I remember when I went down there, I could feel that pressure. Now, that was 12 feet of water, Frank. Could you imagine how the pressure might change if we went down 12 kilometers, 100 kilometers, 2,000 kilometers into the interior of Earth? With all of that rock sitting on top of your head, you'd be increasing the pressure quite a bit. And I mention that because, let's see if I can call up the internet here. I want to show you something called the phase diagram for water.
Okay.
Triple point. Water has something called a triple point, where it can simultaneously exist in equal parts solid, liquid, and gas. But you can't do it at room temperature. You've got to do it. You've got to do it by changing the pressure, or room pressures. You've got to do it by changing the pressure and the temperature. Sorry, my words are sucking today. Listen, here's what I'm trying to say, Frank. All of us have lived our entire life at this red bar right here. This red bar is a pressure of 100 kilopascals. And we understand how water works at surface pressure of Earth. We understand that water will freeze at 0 degrees Celsius, right? And we understand that water will boil at 100 degrees Celsius. And so we're used to it being cold as solid, warm is liquid, and hot is gas, right?
Yep.
But notice, Frank, that if you change the pressure, like let's say we were to go to lower and lower pressures, there eventually comes a point near 1 kilopascal where water cannot exist, H2O cannot exist in a liquid water phase anymore. It actually goes directly from ice to gas. For instance, here's something interesting about Mars. Mars is colder than Earth, right? Its temperature is like -40, -50 degrees Celsius. But because the pressure on Mars is so much lower than the air pressure on Earth's, if you took a cup of water and exposed it to the Martian atmosphere, it would boil at -40 degrees Celsius. That cup of water would boil at -40 degrees Celsius because there is so little air pressure keeping the water molecules in a liquid form. So, Frank, that means whether something is a solid or a liquid or a gas kind of depends upon pressure, right? Look at something else that's interesting. If we were to find a patch of ice or water down in the interior of Earth where the pressures are highest, somewhere above 1 billion pascals, the pressure becomes so great that you force water into ice form no matter how hot it is, even if it's at 350 degrees Celsius. So what that gets me thinking, Frank, is whereas we would normally think the liquid outer core should be hotter, it just can't be true. It's got to be that the warmest, the hottest place on Earth. Shit, hold on here. I'm just trying to start up my slideshow. Function F513. The hottest point of Earth has to be the very center of Earth. The reason why it's solid, even though it's warmer than the outside, is because the pressure is going up so much that you're forcing the liquid metal back into a solid form. So here your intuition was wrong, Frank. The solid inner core is definitely going to be hotter than the outer liquid core. It's about pressure. It's about changes in pressure that affect that.
Alrighty.
It turns out that this stuff has, by the way, I want to talk about what a rock is, but I also want to talk about planetary magnetic fields because I always forget to come back to them. Do I have a picture of magnetic field generation? Yeah. Let's talk about something interesting about the Earth's interior. I want to talk to you guys about how an electromagnet is generated because it's related to how Earth's magnetic field is created, okay? So this is a cartoon of a child's toy called an electromagnet, okay? And the way an electromagnet works is you take a 3-volt battery, like a D battery, and you attach a wire to it. And you guys remember that I told you that when moving charges, when electrons travel down a wire, they generate a magnetic field that's usually in a circular form around the wire, okay? Now, this is just a lump of iron, which is a ferromagnetic material. Ferromagnetic means I am capable of becoming magnetized if you magnetize me. Now, what happens is as the little coil of wire is wrapped around the lump of iron, it generates a kind of wimpy dipole magnetic field. But the wimpy dipole magnetic field magnetizes the iron, and then you get a wicked powerful magnetic field. And this is basically how an electromagnet works. You use the wimpy ass magnetic field of your wire to magnetize the solid lump of iron. And then the magnetized lump of iron creates a very potent magnetic field. So you kind of get more bang for your buck. You see what I'm saying? If you think about it, that's not very dissimilar to the interior structure of Earth. Because if we go back a few pages here, we have an outer liquid core of Earth, which is probably so hot that it generates lots of free ions and charges, right? And then as Earth rotates and those charges slosh around, your inner solid core is a lump of iron, which then creates a potent and very powerful magnetic field, which I am not drawing very well. Let's summarize this as 2 conditions for a planetary magnetic field. We're going to come back to this later, but this is an important concept. So this just relates to the fact that we have an outer liquid metal core and an inner solid metal core. Okay. This module is called 2 conditions for a planetary magnetic field. The first condition is that you need a hot interior, particularly with a liquid metal core wrapped around a solid metal core. But people believe that that warm liquid metal core is a big component to the generation of Earth's magnetic field. The second condition is you need the charges to circulate around in the interior of the planet. So you also need rapid rotation. Rapid rotation creates the current by circulating the charges around the solid metal core. The name of our leading theory of the planetary magnetic field generation is known as the dynamo effect. The dynamo effect is not well understood, but what we do know about it is about 10 million times more complicated than this crappy thing that I just told you right here. This is basically just your first pass at understanding how a planetary magnetic field is created. It's known as the dynamo effect, and you can Wikipedia it if you are brave, okay? Which planets do you think would meet these two conditions? So if we have like, I don't know, if we have Mercury, Venus. Well, actually, you're not ready to see which planets meet those conditions yet, because as yet, we haven't talked about the interior heat of the other planets. Let me do a couple of other fun modules with you before we go forward. I want to address the concept of rock. Most planetary crusts on Earth is made of granite. Here's a block of granite. I got a question for you guys, something to get your noodle ticking here. What the hell is a rock? Like, you think you know what a rock is, right? Like, I know what a stupid rock is, but what is a rock? Wait, I've got a better rock here. I found this at Goosewing Beach. It's just a really nice rock, and I took it home with me, and it's on my kitchen table, and I look at it every time I eat cereal. What the hell is this made out of? I mean, this is definitely granite, right? Do you see those little black flecks in there? Those are called feldspar. I have geology colleagues, and they teach me about rocks. Otherwise, I wouldn't know that much about it. Little flecks of feldspar. What the hell is a rock? Does anyone know from their geology class? A rock is an aggregate of minerals. That's what a rock is. A rock is an aggregate of minerals. Oh, is that a rock, Andy?
It
What the
is. This is Morton Nice.
Oh, wow. Wow, that's a piece. Where'd you get that?
Morton, Minnesota.
Are you a rock hound?
A what?
People who are interested in rocks, who like rocks, are called rock hounds. They go out and they collect samples of rock, or are you just like me and you thought it was cool, so you brought it home with you?
Exactly that one. And then also I brought it home for Dr. Burns.
No way. So you took Emily.
That one.
Emily
Yep.
Burns is one of my geology colleagues, my friends, and she's taught me lots about rocks. See, I'm more of an astronomy guy, so as I get further into geology territory, I get a little shakier, and she's taught me a lot about rocks, but she taught me something more important than just about rocks. She taught me why rocks are cool and why it's interesting to study geology. You have a laboratory all around you, right? And unlike astronomy, where I can't touch the stars, you can take a walk through your local woods and find bits of rock, and you can start by asking yourself simple questions like, is this metamorphic or sedimentary or igneous rock? Where did this rock come from? How old is it? What's it made out of? And there's the history of Earth is buried in rocks all around us.
Professor Britton, just one more point too.
Yeah.
That's actually one of the oldest rocks on Earth is Morton Nice. It's 3.5 billion years old.
That's amazing. Yeah, Earth tends to have a very young surface, so there are only a few places on Earth where you can find rocks. That's great. That's a big sample too, huh? So are you
Yeah.
taking the geology class right now? That's beautiful.
No, I took them years ago.
Oh, wow. That is
Yeah.
very, very impressive, Andy. I love it. Let's break down what we're talking about here, and let's look at rocks from a different point of view. So here's a piece of granite, and I wanted to analyze, not all granite is the same, by the way, but this is a typical chemical makeup of the different, this is what I mean by an aggregate of minerals. Silicon dioxide is a mineral. Dialuminum trioxide is a mineral. Potassium oxide is a mineral. And you can see that this bit of rock is made up of a whole bunch of percentages of different types of minerals. But the mineral that it's made up of mostly is silicon dioxide. Silicon dioxide and silicon tetraoxide, which is a silicon with 4 oxygens stuck to it, taken together, these make up the greatest percentages of the rocks that we find on Earth. I don't know what the exact mineral composition of Morton gneiss is, Andy, but I bet it's made up of silicon dioxide or silicon tetraoxide. It's telling me my internet is unstable, so watch out here, guys. Here's an
Yeah, you
interesting.
froze for a second.
Oh, I did?
Yeah.
The message I had was silicon dioxide and silicon tetraoxide are what we mean when we say the term silicates. Here's an interesting way to look at it. What would happen if you vaporized the crust of Earth? You would discover that if you vaporize the crust of Earth into a puddle of atoms, that almost 50% was in the form of oxygen, 30% was in the form of silicon, and the rest of it was little trace bits of metals like iron, calcium, sodium, potassium, and magnesium. The overwhelming majority of the crust of a planet is made of silicates, silicons stuck to oxygens. I wonder if we could find the chemical composition of Morton gneiss, Andy, since you brought it up in our class, just as a kind of cool comparison. Now, do I spell it M-O-R-T-O-N? Is it G-N-I-G-N-E?
E-I-S-S, yeah.
So let's see if we can find the mineral composition of Morton gneiss, which was Andy's sample there. And let's see if they give us the... Okay, well, maybe we could just click on gneiss and that will help us find it. Let's look at the mineralogy of it, if we can. Oh, man. Here we go. Silicate minerals is what they say. So if we click on silicate minerals, that's when we get silicon dioxide. So silicon dioxide, Andy, is the primary, probably the primary mineral structure of that rock. It's the small variations in the minerals that give rocks their different textures and appearances and properties. Anyways, what's the takeaway that I want you guys to remember? If I say rock, you should think silicon dioxide or silicon tetraoxide, but mostly silicon dioxide. Silicon and oxygen smushed together, okay? That's what the hell a rock is. Rocks are lower in density than metals, right? Do you guys remember what the typical density of rock is? If you don't, look it up in your notes there.
Three grams per cubic centimeter.
Good. And how does that compare to metals?
Metals are 7.
Good. Okay. Let's look at the different planets in our terrestrial zone. Let's bring this back to the solar system class again. And what if we tried to look at the interiors of the other terrestrial planets? This is a slide from your book, which is extremely, extremely illuminating. Let me put your faces down here. Okay. Take a look what's going on here, students. They're showing you the interior layers of the other terrestrial planets, and they're showing them to you by density, which is crust, mantle, core. But they're also simultaneously imposing upon them the depth of the planet's lithosphere, where the lithosphere is shown as a dashed black line. What's cool about this is it has 2 messages for you, the student. The first message is this. If I just look at a terrestrial planet by chemical composition, they all are kind of seeming the same. All terrestrial planets have a silicate crust on the outside, a mantle, and then a metallic core. Earth, Venus, Mars, Mercury, Moon. They all have crust, mantle, core. So if you look at the planets by density, you really don't learn much. If you look at them by strength or rigidity or by the depth of their lithosphere, then you learn something interesting. You learn that Venus and Earth have thin lithospheres, but look at the lithosphere of Mars. It extends down to more than half its radius. Do you want to know what that tells me? It tells me that the interior of Mars is frozen solid. It's as if your pie crust was all crust. It's just going all the way down into the interior of the planet, and there's no warm, gooey, convective rock there. Mercury has a medium thickness lithosphere. Mercury's weird because it has an obnoxiously large metal core, and the moon is weird because it has an obnoxiously small metal core. The moon's lithosphere extends all the way down towards its center. The moon is completely frozen solid. The takeaway from that lecture point is that not all planets have the same amount of interior heat. So let's make a big deal about this. There are two types of planetary heat. There's the surface temperature of the planet, and that's got nothing to do with its interior heat. The surface temperature is mostly about your distance from the sun. It's also affected by your atmosphere, and it's also affected by the planet's reflectivity. But mostly, the number one thing that determines the surface temperature of a planet is its distance from the sun. I'm here to tell you that I'm interested in a completely different type of temperature, the interior temperature of a planet, or what I will call the interior heat of a planet. The interior heat is completely unrelated, and the interior heat is basically related to, well, there are three things that determine the interior heat of a planet according to your book. Let's just look at a cartoon really quickly. The interior heat is affected by three different things. The first thing is accretion. And I don't know if you know what the word accretion means, but it means to stick together. Like if you ever take a snowball and you roll it along the snow to make a bigger snowball, you are accreting snow. Accretion means the heat of formation. When our planet first formed, it was probably a disk of rubble and rock that was spread out over a great area. If I could just get my formation of the solar system lecture, I could help explain that here. What the Earth looked like before it formed. Where am I here? I have a nice picture. This is probably, oh wait, am I sharing screen with you guys? Slide 40, no, I'm not. This slide 49 is probably what Earth looked like when it first formed. It was probably a swirling disk of gas and little bits of sandy, rocky debris. And gravity was probably pulling the planet down on top of itself. Probably the gravitational forces smushing all of that rock together. When Earth first formed, it was probably so warm that it was actually molten rock at its surface. It was basically like a ball of lava. And Earth was probably glowing when it first formed. So one of the things that affects how warm a planet is just the accretion, the amount of material that's there to form it. Over time, the interior of the planet can stay warm from two processes. Differentiation is where heavy metals sink and light materials buoy up to the surface. So that's kind of like a friction. People make a big deal in geology about the differentiated layer of Earth. The differentiated layer of Earth means the fact that it looks like a kind of lollipop that has crust on the outside, mantle on the middle, and iron in the center. When Earth first formed, it probably didn't have such a segregated, layered way. You know, kind of like when you leave your salad dressing out and the oil and the water separate? Same thing. Over time, the metals are going to separate from the lighter rocks, and they're going to segregate it into differentiated layers. Also, Earth has a tremendous quantity of radioactive materials in it, and these radioactive nuclei can help continue to heat a planet long after it's formed. So these three things, let's, how do I get out of this share here? Stop share, okay. The interior heat of a planet is related to these things. It's related to basically, in a simple version, the interior heat is related to the size of the planet. But if you want to get down into the weeds and go further than just the size, the three things are the accretion, which is basically the heat of formation. There's the differentiation. Differentiation is once again like the convection or the lava lamp effect. We'll write it like this. We'll write it as heavy metals sink light silicates rise. So the light rock rises, the heavy metals sink. That says light silicates rise. I didn't write that very well. And then the third thing is radioactive decay. That's where your uranium nuclei and your radon and your plutonium nuclei spontaneously break apart and release gamma rays and other types of radioactive energy. Here's one more big takeaway that I'm trying to impress you guys with. And I'm going to put this as a special note at the bottom. I don't want to say the thickness, I want to say the depth of a lithosphere. The depth of the lithosphere, how deep your lithosphere goes. The depth of the lithosphere is a measure of the interior heat
Brendan, you'll have to angle the camera down.
Thank you. The depth of the lithosphere is a measure of the interior heat of a planet. That's the big takeaway I wanted you guys to get from this little section here. This is one of the reasons why the Mars InSight lander is so interested in measuring Mars quakes so that they can get a precise estimate of the depth of Mars's lithosphere. We expect that it runs quite deep into the planet and that Mars is essentially frozen solid.
That's a pretty simple saying or statement, but it sounds like there's a lot to that.
That's the right idea. You can boil the stuff down to simple concepts or simple statements, but there is a lot that goes into the understanding of it. And you've got to take time for the ideas to digest. Let's see if we can practice here. So let's look at the lithospheres of the planets again in slide 21. Which planets should have warm interiors according to slide 21? Which of our planets should have warm interiors?
So the greater the lithosphere, the hotter
The
theory
thinner,
should be?
the thinner the
Oh, the
lithosphere.
thinner. Okay. So which planets have hotter interiors?
Yeah,
Earth and Venus.
that's right. Exactly. These planets should have the warmest interiors. These planets have cold interiors. Mercury's lithosphere doesn't look quite as thick here, but Mercury's a little bit weird. People usually say that Mercury does have a thick lithosphere. So these planets are cold. or frozen. These planets have warm interiors. Which planets should be capable of having a magnetic field?
Earth, Venus.
Wait a minute. What are the two conditions for a magnetic field? You just learned them.
Hot interior
Hot interior.
and rapid rotation.
Earth has a 24-hour rotation, and that seems to be rapid enough for a magnetic field. How about the rotation of Venus? What's up with Venus's rotation rate? You learned about this last class.
Yeah, but, it's
It's like 279 days, I think.
243 days.
Sorry,
Yeah, it was close.
243 days.
It was a lot for it to rotate.
So, well, would we expect Venus to have a planetary magnetic field? No way. It rotates. It's warm enough, but it's too slow. On the other hand, Mars has a rotation period of 24 hours, so it rotates fast enough. But look at its lithosphere. It's so deep that Mars is frozen, and this is why today Mars no longer has a magnetic field. The moon has absolutely no magnetic field. Mercury actually has a weak magnetic field, probably because of its obnoxiously large metal core, but its magnetic field is hundreds of times weaker than Earth's. Some planetary scientists, though, do make a career out of studying Mercury's wimpy magnetic field. Mercury is just weird. It does a lot of weird things. Okay, let me clear out the drawings and stop.
Hence why it's called Mercury, because Mercury is so volatile.
Well, I don't know if Mercury's volatile. It's a liquid at room temperature, right? It's
Well, yeah, but like
toxic.
Mercury thermostats. I mean, it's like volatile might be too polarizing of a word.
Yeah, for me, volatile
It's
means
temperamental, I guess.
Okay, I see what you're saying. Yeah, but for me, volatile means able to go into a gas quickly at low temperatures.
Yeah.
Like water is a volatile, so is carbon dioxide. Carbon dioxide is volatile. But
Okay.
Okay, we are not done with terrestrial geology. We've got a lot more to learn, but we've certainly had a snootful today, right? We're gonna do a lab on the moon. How do you guys feel about taking some break time? You into that? Yeah, I think I like that too. So let's give ourselves a good, let's start at 1:15. Give ourselves a good healthy break. You guys like that? Today's lab isn't very long. Okay, so at 1:15, we will return and we will do our moon craters lab. I'll see you then. Okay, everyone, welcome back. It's time for lab number 9, Lunar Features, where we're going to use this moon map that I've provided for you on Blackboard's lab number 9. We'll record data on our Lunar Features sheet. Oh, and we do need one more thing. We need a photograph of the moon. And the photograph of the moon that I want us to use is by H.R. Astro. And I did not include that, but I will. Just a moment while I find it in my junk pile here. Now, what in hell did I do with that thing? Sorry, guys. Of course, I would forget something. That would be just like me to forget. I found it. Okay. This is a photograph of the moon that I can share with you here. Usually I hand out physical copies. I don't think I attached it, but let me fix that. HR. Okay, I'm going to send you guys a link to the photo that we want to use here. I should really upload it for the purposes of night students. Cancel. See if you can grab that photograph real quick. And meanwhile, I will save it. I thought I already did this. I'll save it in labs. Isn't that nice? Oh, look, I already have it here. Okay. And let me just edit the labs here to include this for the students later. Moon map, lunar features, browse local files. Okay. It should also be uploaded to Blackboard now for the night students. Now,
Ava was wondering if we just submit the data sheet.
that's correct, Ava. Sorry, I didn't see your chat. We're just going to submit the data sheet today, nothing else.
Or is that other paper under lab?
Well, it's in the chat. You can click on the link, or yeah, you can go to the Lunar Features lab. You'll notice if you go to Blackboard.
Just a picture of the moon.
Huh?
You see a picture of the moon.
Well, you're going to need that, right? You're going
Yeah.
to need several different things. Ava, the only thing you actually need to print out is the Lunar Features PDF. These are the two halves of my moon map, and this is your waxing gibbous moon by HR Astro. Sorry, guys, I ate some spicy Indian food, and now I'm coughing to death. Are we all clear now? Andrew, are you clear?
Yeah, I'm clear.
Okay, all right. So let's start by seeing if I can connect. And I want to talk about the point of today's lab. The point of today's lab isn't to read the names of the craters off of the map. The point of today's lab is, you know, wouldn't it be cool if you could take a walk on a moonlit night with that special someone in your life, and you could look up at the nighttime sky and you could say, do you see that right there, baby? That's Mare Crisium. Now, you would be a cool person that people would want to get to know, okay? And so the idea is, could you use the map to actually look at the moon, either with your naked eye or with your telescope, and identify one of these features? And that's what we're going to try to do for the most part today. We'll kind of follow along with the instructions. Let's start by seeing if I can share to my phone without too much drama. Okay. Share screen, iPhone, boom. I've got to install the dumb plugin again. Be helpful to have a ruler if you've got one of those. And boom, we got action today, guys. This is great. All right. So I've got my lunar features map up here. Okay. I've got my photograph of the moon, which you guys probably all have digitally. Ava, if you're using it on your computer, that's fine, but you may want to try to rotate it. Do you guys notice here, there's kind of a butterfly-shaped Maria? There are two types of terrain on the moon. There's the Maria and there's the highlands, like the Scottish Highlands. The highlands are the heavily cratered terrain, and the Maria are the dark gray splotches, which are basically volcanic rock. Can you guys identify the butterfly-shaped Maria or the heart-shaped Maria here on your map? What's that Maria?
Tranquilitus.
Tranquillitatis. And that's one of the places where the astronauts landed, right? That's Tranquility Bay. Mare Tranquillitatis means the Sea of Tranquility. Now, do you see how Mare Serenitatis is rounder and it's below? We need to rotate this map if we want to do it right. I'm rotating the photos. I'm sorry, I'm rotating the photo so that Tranquillitatis sits on top of Serenitatis. And now it matches my map. So I'm kind of getting my lab feng shui all set over here. Let's see how my lab feng shui looks. Make some room. If you have enough room on your desk at home, I've got my data sheet, my photo, and my moon map. All right. First, we're going to remove the photo and we're just going to look at the map and we're going to try to understand some of its features. When telescopes take images of an object, the image is often inverted and upside down. So you're going to see that the northern latitudes are positive. It goes positive 10 latitude, positive 20 latitude, positive 30 latitude. That's going down. Going up from 0 degrees latitude is negative 10, negative 20, negative 30. The longitudes are also reversed with positive 10. Well, actually, it's eastern based, so east is on this side. So positive 10, positive 20, positive 30, negative 10, negative 20, negative 30. Let's get some info down on our sheet here. Let's put our name. Let's put lab 9. People are still submitting labs to the wrong thing. And this is AS1010. Put your section down there too, if you don't mind. First thing it wants us to do is identify the crater at negative 20. This is longitude. And positive 10 latitude. Okay, guys, go. Look at your map and tell me the number of the crater at negative 20 longitude and positive 10 latitude on your map. Use the handout I gave you and show me what you can do. Meanwhile, I'm just going to chill for a sec. Work on my feng shui.
So negative's at the bottom.
What are you which one are you talking about?
The one that we're doing. So like negative would be at the bottom of the equator.
You mean negative latitude or negative longitude?
The longitude.
The longitude measures east to west, left to right, not top to bottom.
Oh, all right.
So negative longitudes are to the right, Andrew. Can anyone find the number of that crater?
Is it 116?
It's not 116. 116, I believe, is, well, it's not really clear to me what 116 is, but it's some other crater.
Oh, 74.
That's right. It's 74. So notice that he went minus 10, minus 20 in longitude, and that's positive 10 latitude, and they intersect there at 74. Now we've got to use the legend. What's the name of our crater?
Copernicus.
One of the most famous craters. You can actually see it on the photograph here. It's just barely in the shadow here. That large crater is Crater Copernicus, one of the largest craters on the moon. What phase is the photograph in?
Waxing gibbous.
Good.
Oh,
Do we have that?
Wait, where is it? I can't see that. Where is that? Oh, Waxen. Gibbous.
Gibbous.
All right.
Okay, they want the Maria visible on the photograph, and we have to pick 5 Maria on the photo. Sorry, my N looks bad. Okay. Can you guys identify some of the Maria? Why don't we choose like 1, 2, 3, 4, 5. Let's pick those 5. What are their names?
Maria Tranquillitatis or whatever.
Yep.
Maria Nectaris.
Nectaris. This one's
Maria.
Fecunditatis, Mare Crisium, and Mare
Mare.
Serenitatis.
All right.
So let's do them in order. So we have Mare Tranquillitatis, Serenitatis. Did I spell that right? Serenitatis, yep. And over here, we'll do those top 3. Mare Nectaris, Fecunditatis, and Crisium.
Oh.
I'm trying to remember the name of there's a famous Italian astronomer who named most of the craters on the moon. Well, he's not that famous because I can't remember him. Who named the craters on the moon? No. Oh, I'm forgetting the name of this Italian astronomer. Oh yeah, Giovanni Battista Riccioli. Riccioli. Jeez, I can't do Italian, guys. Where's my Zoom? There we go. How do I chat? This is the fellow here in the chat who named most of the craters in the moon, if you're interested. Okay, so let's keep looking here. The next thing we have to do is identify some mountain ranges. We want to make sure we can identify the mountain ranges in the photograph. Let me turn down the lamp a little bit here. That's too much. Okay. Do you guys see this feature that you're looking at here on the photo? This is a mountain range. Let me show you a kind of cool old CIA analysis trick here. You'll notice that if you look at the direction of the shadows on my map, can you guys see how the shadows of the craters are on the left-hand side? Look at the shadows on the mountains. They're not on the left, they're on the right-hand side. That tells me that the craters are an intrusion. They go down into the crust or the lithosphere. These mountains are an extrusion. They poke out. And so if sunlight is coming from up here, from the direction where my pencil is, it hits the mountains and makes a shadow on the far side. But when the thing goes concave down into the surface, the shadows are on the left side. That's how you can tell if something's poking up or sticking inwards. So when we have these craters, we can actually find them here on the map. You'll notice they put letters on both sides. This mountain range runs from D to D. And when we consult our legend, what do we discover the name of those mountains are?
The Apennine Mountains.
Yeah, the Apennine Mountains. They're all named after famous mountain ranges in Europe and other places. Apennine Mountains. So let's get down the Apennine. Something noisy is happening outside. I think I spelled this right. Let's look for some other mountain ranges together. Oh, sorry. Andy, do you have an issue there?
Yeah, I couldn't see it. I got it.
Can you guys see any other mountain ranges? Why don't you guys look for, this is a mountain range right here. Use your map and tell me what letters that mountain range is. I'm trying to hold this steady here. Oops.
Sadness Istenum.
No.
Caucasus.
Yeah, what letter is that, Jake?
F to F.
That's right, that's F to F. And F to F, you can see it's just below the Apennine Mountains, is the Caucasus Mountains. This lab is just a bona fide excuse, just a shameless excuse to look in features and craters in the moon. That's all it is. That's fun. We got to get one more mountain range. Where's Jake's little face here? You seem to be good at this, buddy. Why don't we try to get one of the ones, maybe it looks like one of the ones down here.
B to B, is that what it is?
That's what it looks like it to me.
Yeah.
Alps, the Alps.
The Alps. Okay, so they named them after the Alps. We can get down with that. Focus. Okay, now we're going to try to get some different types of craters. Let's find some examples of flat bottoms. You'll notice that some of the craters, like for instance this one, can you see how it looks like it's filled in? That probably suggests that at some point it might have had a bumpier interior like this one, or maybe even like this one, but probably a pool of lava soaked into there and covered up the surface. The fact that it's so much smoother than the surrounding mountains suggests that there was some lava flowing across this at some more recent geological time. So that would be a quintessential example of a flat bottom. Can you guys use the map and find that? It's right underneath the Apennine Mountains. What number would that be? This guy right here.
$14.
Yeah. Oops. Sorry, my thing is freezing up here.
Oh.
14.
Archimedes.
Archimedes. Right. He famously measured the gold crown in the bathtub, right? He said, Eureka. Let's get that as a flat bottom. Let's see if we can find another good flat bottom. Yeah, Andrew, how can I help?
I didn't really see it, like, sorry.
It's okay.
Got it. I got it.
All right. I'm going to see if I can, oh, I was hoping to get more of you in a little box there. Okay. Can I show you which one of the most famous flat bottoms on the whole moon? This is a very famous crater on the moon. You can see it right there. It's a classic flat bottom, totally smooth at its interior. Can you find that one for me?
Is that Plato?
Yeah, that's number 230. You got a knack for this, Jake. You have a.
I'm bad at math, but I'm good at geography.
Yeah, cartography could be your thing.
Play-Doh.
Oh, the two go hand in hand, by the way. 230. Usually you get good at math when there's something that you want to do that you like that involves math. That's how it works, right? No one just starts off by liking math for math's sake. It's a tool. Like that would be like falling in love with a hammer. What kind of freak would fall in love with a hammer? You like hammers if you know what you can do with a hammer, you know? Play-Doh. That being said, I do love my tools. Okay, so let's see if we can find one more good example of a flat bottom. I'll poke around the moon here.
I found one up in
There was
the.
one near the top that I kind of liked.
Okay, yeah. Well, why don't you guys help me pick one? Can you tell me which one it is?
I found 179 Longo Montanus.
Okay, hold on. Let me see if I can find. Is it visible on the photograph? That's important. It has to be visible on the photograph.
I was trying to match up the photograph with the. I'm not sure on the actual map, but it's there in the photograph.
Can you? Is it in my field of view on my camera here?
No, it's not.
Is it anywhere here? It has to be in the photograph for us to choose it. That's all. Which, like for instance, Longo Montanus. Do you understand? I don't want it just to be visible on the map. I want it to be visible in the photograph first. The idea being, what if we were looking through a telescope together and we saw this craziness?
Well, for me, it's all the way up on the top, but it's on the right side.
Is it past
But-
the shadow?
It's right. Yeah, it's right around there.
Like this guy, or?
No, I think I have a different photograph than you.
It's probably upside down, right? Your photograph is upside down.
There it is. I found it. Yep.
Where? That
Yep,
one?
that's it.
Wait, that's the one we were just looking at. That's Play-Doh. It's upside down.
My photograph is upside. Oh, all right.
You got to rotate, Andy. It's okay.
Well, it's on the
Yeah.
computer screen, so it's tough.
Someone else. Oh, shoot. Someone else had. Yeah, I'm working. Someone else had a. Jake, did you say you had one you liked up here, or someone?
I did, but I just realized mine is flipped the wrong way on the computer as well.
Okay, guys, we want to pick a flat bottom. If you have one, you can tell me one. I mean, there's that.
Well, no. 179 might be there.
Let me see where one. Can you help me find?
If you look at the bottom of the picture, Andy, that might be what you're looking at.
First of all, can you show me where 179 is on the map? Because now you've got kind of piqued my curiosity here. Oh, there's
It's up.
179.
Yeah. Yep.
So would 179 on the picture be the one with all the, like,
This
the dot?
No, this is 179 right here.
Oh, that's it.
Yeah, mine was upside down. I didn't realize.
Okay, hold on. What about this one?
That one right there. Yeah, that's
This
the
one
one
is
I'm talking about.
This is a better flat bottom. Well, you know, it does have some craters inside. I don't think.
What about the one to the southwest of that?
Yeah, that's the one I was looking at.
Oh, this one?
Yeah.
I'm pretty sure that is that's the big crunchy one we were just looking at. So that would be 185. So this guy right here. Here's how I know. Can you see how this crater has like some Mickey Mouse craters on the rim?
Uh-huh.
Mickey Mouse ears? You can see the Mickey Mouse ears here and here.
Oh, yeah.
That means that's 185. So what's 185? Let's go with that one. McGinnis. Okay, cool. I like your choices, guys. Okay, a lot of craters feature something called a central
Oh,
peak.
I can't see. There we go.
Did I spell
Thank
that
you.
right? Yeah.
Yeah.
Okay. A lot of sometimes craters feature this little mountain in the center called a central peak. You can see one there. You can see one there. The central peaks are kind of interesting. They're a wave phenomenon or a slapback when an impact strikes the crater and then slaps back. It basically liquefies the rock, and then the rock sort of solidifies as a little mountain in the center. I promise next class I'll explain the central peak thing to you guys a little better. But you can see a lot of these craters seem to have this sort of little dimple in the center, like that guy there. That's a central peak. I wonder if we could find that on some of the ones up here are kind of hard to find, but we just had 185 right here, right? So this guy is a central peak that should be just below it and to the right.
226.
I think it's
To your
280.
left.
Sorry. So there's 185. I think it's 284, right?
Oh, okay.
That's my guess.
Yeah, that looks better because it's more the crater's more defined.
This game is hard to play. Now that's one of the most legendary central peaks in all of the moon's history. It's crater Tycho. So we definitely want to start with that one. Hard to appreciate just how cool crater Tycho is. Let me show you an up-close picture of crater Tycho on my screen. Actually, I can do you one better. So this is what crater Tycho looks like. In fact, I think crater Tycho is so cool that I had one of my colleagues print a 3D model of crater Tycho. I got this from NASA, from the NASA website. I got a model of crater Tycho as a rapid prototype file, and I actually had it printed out on a hard form plastic here using a 3D printer. The ratio is like 27 kilometers to maybe a half a kilometer tall or so. Sorry, no, the central peak it's 27 kilometers to maybe 3 or 4 kilometers. And this is the material. It would have been nicer if I painted this surface. Sorry, guys, my thing's freezing up. That's crater Tycho right there. Famous central peak, little mountain right in the center. All right, let's see if we can find a few more central peaks. Here's a cool one that should be pretty easy to find. We found that crater before. I think that was maybe Archimedes. Let's look just to the left of that, below the Apennine Mountains. Looks like crater 17, I think. And that's Aristillus. Let's pick a nice central peak for our last one. I don't know if you guys have a preference, or I kind of like these.
That's at the end for Aristillus.
I'm sorry, could you say that again, Andrew?
Oh, I'm all set. I
Okay.
already see it.
All right. Notice that there are these 3 craters in a row that look like a little snowman. That one at the top, that seems to have a pretty classic central peak. That should be pretty easy to find on a map, don't you think?
Is that 19?
Yeah, that's 19.
Yeah, it's like right on the crease, right?
Yeah, or a little above. Arzakel. Arzakel. Now, the central rays are going to be tough.
Oh, I can't.
Sorry, went a little too fast there.
Yeah. Got it.
When craters form, they have some different structure to it, right? So the rim is the outer wall of the crater. Sometimes they have a central peak in the middle. Oftentimes, some of the material gets splattered out, and the material that gets splattered out kind of forms these spokes that they look like spokes on a tire, and they're called rays. Sometimes they're called ejecta. But if you move really, really far away from the crater, as it gets farther and farther and farther away, in an aerial shot, sometimes the rays can just kind of end up looking like some gray fuzz that kind of surrounds the crater. So when you're really, really far away, like we are in this photograph, it might just look like some fuzz. So the rays are really tough to find here. I was thinking that maybe like, see how this crater has some gray splatter around it? Maybe those would be considered rays. How about this one here? That has some stuff surrounding it.
The one at the north end of D.
Sorry, say that again?
North end of D. Be number 97, I think, on the picture.
Number 97. Number 97 is Eratosthenes. I think that's probably good. Let's check a Google image of Eratosthenes to see if it has good crater rays. Crater.
This one. This one right here, Brendan.
Yeah, I see. It's Eratosthenes, right?
Okay.
Let's look at a picture of Eratosthenes.
Yeah, I think so. Yeah.
Hold on. Oh, bloody hell. This is okay. Let's just go with our intuition here. Since this takes the, you were saying the one at the top of the Apennine Mountains, right?
Yeah, I believe so.
So you're saying
Yeah.
this?
Yeah.
Okay. I don't
know. It looked like on my picture, it looked like there was some splatter, but it could be like the one next to it. I think that's 267 or 269. Looks like there's a bit more defined, but I don't know
I
if
can't
that's
even
just.
see. 269 almost looks like a little mountain or something. It's
hard to tell.
Right.
Like
You might be right
said.
that Eratosthenes, the crater, has rays. I wanted to see it for myself so that I could.
What about the one to the right of that, the big one?
Oh, Copernicus, I think definitely has rays. I was just trying to check on the internet. See if you guys can help me here. Copernicus crater. I'm almost positive Copernicus has rays just from seeing other photographs of it. Let's see if we can. Yeah. Okay, I'd say Copernicus is a pretty good example because look at this photograph here on my screen. Can you guys see how there's like spokes that radiate out in all directions here? That definitely has some rays. So we'll double dip with Copernicus, okay? We could go with Eratosthenes or Eratosthenes or Eratosthenes. It
Wait.
looks like Eratosthenes, but it's really Eratosthenes. That was Joel's suggestion. I'm willing to go along with it.
Is that an N or an R?
Well, you can follow along by finding this crater, right? This crater is 97. And 97 is Eratosthenes.
Oh, Eratosthenes. Oh, now I see it.
Okay, maybe we'll go with this guy up here as our last crater ray. Sorry, I gotta focus my stupid fucking camera here. Sorry, pardon my French. Okay, so there we go. This guy is somewhere between Mare Vaporum and Sinus Medi. (283) is our man. Ooh, that's cool. Try Snicker. Try. Okay, you guys got this?
Yep.
So we're not going to do the height of a mountain. We're going to skip that part, but we will do this last bit, which I think is interesting. It shows us a way to measure the size of a lunar feature. Now, look, when you look at a cool thing like Crater Copernicus, a question that you might ask yourself is, how big is that thing anyways? Is it the size of Rhode Island? Is it the size of Texas? Is it the size of Mars? I have no idea. But there's a cool way to figure that out. And that's that we know the true diameter of the moon, and we can compare it to the measured diameter of the moon and create a scale factor. So I want you guys to work with me here. The true diameter of the moon is 3476 kilometers. And what we're going to do, sorry?
What's the question name for that? Because I forgot to write that down.
When you say that, what is that?
The scale photo. Oh, I just need to write that down.
And we're going to divide it by the measured size of the moon of the photograph in millimeters. So right underneath, we're going to measure the photograph of the moon. I'll use my ruler here. We'll try to measure it the longest way. Start 0 up top there. How many millimeters would you guys say? Let me see if I can get my lighting correct here. How many millimeters would you say this thing is?
$224.
Good, Noah. I like it. So that's 224 millimeters. Noah, can you divide those up for me and get my scale factor? So do 3476 over 224. 3 sig figs will suffice because you've got 3 sig figs here.
15.5.
And what are the units of that scale factor?
I don't.
Pardon?
Are there units? I guess it's kilometers per millimeter, but
That's right. That's how a scale factor works. Have you ever seen a map, Noah, that says 1 inch equals 20 miles or something?
yeah.
Same thing. This says 1 millimeter equals 15.5 kilometers, or 15.5 kilometers per millimeter. Now we're going to choose a few features here. We'll do Crater Copernicus. We'll do the Apennine Mountains. And we will do, I don't know, should we do Mare Crisium? And first, we're going to measure their diameters in the photo in millimeters.
What is that word? I can't see it.
Right there?
Thank you. Yep.
Okay. It's Mare Crisium, which is, excuse me, this stay here. So let's start with crater Copernicus, and let's first measure its diameter in millimeters, okay? So it's kind of in the dark here, but I'll hold this up as best I can. You guys tell me what the measurement is. How many millimeters across would you say that is?
6.
Yeah. I'd agree that's about 6 millimeters. Now, guys, if you multiply 6 millimeters by 15.5 kilometers per millimeter, that'll get you the diameter in kilometers. Oops, oops, ooh, what did I do here? Okay. So can you multiply 6 millimeters by 15.5 kilometers per millimeter?
93.
How many sig figs should I keep?
3.
False.
Two.
How many sig figs does your measurement have?
Oh, one.
So
One.
what should I
Just
round?
1.
So what should I round it to?
90.
Exactly. That's the best you can say. Okay, let's do the Apennine Mountains next. We've got to do it on the photograph, not the map. So this is a little weird because the mountains are curved, but I'll kind of put 0 up here at one end. And we'll measure out to the edge over here somewhere. What would you guys say?
35.
Say that?
35.
Yeah, I'll go with that. This measurement has 2 sig figs. Multiply by your scale factor.
$540.
Okay, and now let's do Mare Crisium. There's Mare Crisium. We'll do it the long way for fun.
$26.
Okay. And now multiply that by 15.5. Sorry, I can see someone chatting me, but 390 says Cam. Okay.
I got 403.
Yeah,
Wait, which is it then? Do I have to do it?
403. 403
All right.
for 400.
400. Because 403 would be 3 sig figs. How does this compare to Rhode Island? Like, what are the dimensions of the state of Rhode Island? That's my drawing of Rhode Island. Sorry. Should we look on Wikipedia? Rhode Island. On the Wikipedia page, they should have what the hell? Oh, I've got videos clicked. Uh-oh. Come on, you son of a bee. All right, look at its dimensions in kilometers. 77 by 60 kilometers. So Rhode Island is 77 kilometers long by maybe 60 across, right? How does that compare with crater Copernicus?
It's smaller.
Right. So the entire state of Rhode Island would fit inside that crater. That sure gives you something to think about, doesn't it, Jake?
That's crazy.
Yeah, right? That's
Like
pretty
1.5
wild.
times.
Yeah, yeah. So that whole crater is bigger than the state of Rhode Island. It would be, could you imagine like how scary it would be to land on the moon and to try to take a dune buggy? Like you're going over a pretty big distance away from your mothership there. That would probably be a bit terrifying. All kinds of mischief could happen, as you know, on any car voyage across the United States. I know that I've certainly broken down in Birmingham, Alabama once when I was on a road tour in my van. That wasn't very fun. So you can imagine it might be scary to take a trip across the surface of the moon, knowing there were no gas stations out there.
Don't
Anyway.
jinx me. I got a road trip in 6 weeks.
Oh, really? All right, okay.
6 weeks headed out to Kentucky.
To Kentucky, huh?
Yeah.
That's gonna be
28th
fun.
of December.
I stayed up late last night watching. I'm a chess player, and my friend convinced me to watch this Netflix show called The Queen's Gambit, and that takes place in Kentucky. So that was Kentucky's been on my mind this evening. Anyways, did you guys get all this? Do you need one more look, or do you guys have all that stuff? That's our lab for the day. We just kind of explored some craters of the moon together. I think that was pretty chill time. So you guys know what to do. You got to keep turning this stuff in, right?
Yeah.
I'm going to have to deactivate the last 2 weeks homework and lab. I just graded them last night. It looks like a pair of pants, Cam. Yeah, I know. I didn't draw the best Rhode Island, but so please make sure you get that lab sent in to me right away. Okay, guys?
Do we have class on Wednesday?
Why wouldn't we? Yeah.
It's Veterans Day.
My
my
day.
Class said that they didn't have it, so I was wondering.
Yeah,
if
my
we-
other class said we don't have it either.
Oh my gosh. You might be right. Well, let's just check.
Veterans Day.
Yeah, Veterans Day is an important holiday. Absolutely, Joel. We gotta thank you for your
Joel.
service.
Thank you.
Yeah,
Joe.
thank you for your service.
I'm not going out and getting all that free crap.
What do you get? Do you get free stuff?
Yeah, like a bunch of restaurants give you like
Free lunch at Denny's or something?
selected menu. I don't even bother.
Well, I don't know, man. No, don't screw up a free lunch. Have you ever heard that saying? Wait a second. You're right. If I crossed it out, that meant I was probably anticipating that we wouldn't have class this week. Let me just verify that because thank you for reminding. Was that Gabby that said that? Who said that to
It was
me?
Kelly.
Oh, Kelly. Kelly, I have no idea what you look like, but thank you for your service as well. Hold on. Let me just. It's November
11th.
Okay, no classes. All right, that's right. So we have, hey, how about that? There is no class on Wednesday. I won't see you guys for another week. That's kind of cool. I forgot about that. Thanks, Kelly. Thanks, Joel, for your service and any others of you who have served as well. I think that's wonderful. That's a good day for us to relax and celebrate our veterans. And we'll get back to planetary geology next week. We got plenty of time. So any other questions or comments? Thanks for reminding me. I guess I don't need to send out an email, but I'll make an announcement on the Blackboard page that says no class Wednesday.
Can I see the paper one more time?
Yeah, sure. Let me see if I can do the phone share. Phone share. Oops. Yes, the gods are with us.
Oh my God. All froze over.
Do you have all that stuff?
Yep, thank you.
All right. Okay, guys, I'll get this thing up to the internet soon enough, and good hanging with you as always. I'll see you 1 week from today. Peace out. Joel, I'm going to read that article, okay?
All right. Hey, I got a question
Yeah.
after you stop recording.
Yeah. Oh, yeah, let's stop that.